Why don't we start, because 9:40 is when I usually start the lecture, so everybody who is going to attend is going to be here. So let me just make a quick announcement. This fellow, I'm sorry, what was your name again? Kid Morrow is from HKN. He's an undergraduate. He's going to do the surveys for the course. In case you're not familiar or this is your first year at Berkeley, these evaluations are used for all promotions of all professors. Every time you get promoted, every single comment you write gets typed up, goes to the chair, and then the dean, and then the provost, and the chancellor, and then it comes back down with comments and other things. So you can mark numbers, but if you want to see the next generation of students for this course benefit from it, put comments, especially constructive comments about how you think the course should be run next time it's taught. So why don't you go ahead and pass? And I believe is there one for the TA? There's a section for the TA as well, or the one you brought in? Right. So if there's a section for TA, then that's Cindy. So you want to write comments on her. Pardon? No, not at all. Is everybody done? Okay. Thank you. When will just so that the students can know, when will the survey be available?
I don't know, actually. It should be soon.
It's after the grades have been submitted, and so it's at least May 20th or something like that. Okay. Okay, so let me start by a few announcements. I think there's no more homeworks, as you all know. The presentation is, as we agreed, is on May 5th. In order to make sure that we can accommodate all the projects, I've reserved the room, Wang room, from 9 a.m. to 11. Okay. So I'm going to ask everybody to show up at 9 instead of our usual 9:30, just so that we make sure we don't run out of time and the projects that are multi-persons can get enough time to present what they have. Is there anybody in the room at least that has trouble attending the 9 a.m.? Okay. I also received a bunch of emails from you that are doing projects, so I'm keeping track of the number. So I'll be so that we can then, at the time of the at the day of the presentations, we can figure out how much time should each presentation take. Just so that you know, May 5th it's not this Friday, but the Friday after, so we're about 9 days away from it. Now, when you give the presentation, I might make some comments, and the presentations day is actually, you can think of it as a little bit of a feedback review thing. If you feel like it, then you want to improve things, there's time between May 5th and 15th where you hand in your project report to possibly take some of the comments and feedback into consideration in the final report. Question?
So it's okay if we don't do that, though? Because, like, I literally won't make time.
No, it's okay. It's fine if you don't do that. But if there's, if you feel like doing it, you're welcome to do that. In other words, what I'm trying to say is, just because you give a presentation, it doesn't mean your report should be verbatim copy of that. If you have time, if you do make progress between 5th and 15th, feel free to include it. Don't feel like you can't put something in the report that you didn't talk about on the 5th. Okay, because I think a lot of the students will be changing things and will be improving, but you don't have to. No, that's not necessary. So, any questions or comments? Okay, I have one other announcement to make, and this is really a side comment. EE 2215B is now available, not that it wasn't available enough places, but the video lectures are not available on podcasts. So if you go to berkeley.itunes.edu, you can watch the lectures on your iPod devices and listen to the lectures on the iPods that don't have video. This became available as of Cal Day, which was April 22nd. It's kind of it's an immaterial announcement as far as you guys are concerned. The semester is almost over. There's 3 more lectures, including today's, and in case you're curious and you want to watch the lectures on your iPod, you could do that now. And I'm sure our attendance will become even lower once that happens. Okay, any other questions or comments? How many of you, just out of curiosity, how many of you have iPods?
It's only work. It's only the big ones.
I see. For video, you mean?
Yeah.
Or you can listen to the audio only?
No, I can't.
It just doesn't work. Okay. All right, and how are you guys doing in terms of your projects? How many people are done? Excellent, excellent. And how many people are not done? I guess the set minus the other ones. So don't have to raise your hands. Okay. Let me put the microphone on and let me get going. So we have a lot to cover today, and we lost a little bit of time to HKN. Okay. I feel like an astronaut with all this equipment hanging. Okay, so what we talked about last time was transform techniques, right? In particular, we had finished talking about space domain prediction type techniques, and we talked about the fact that in transform techniques, you're essentially representing your image as a sum of a bunch of basis functions. And we'll elaborate on that a little bit more today. And essentially, there is an optimal transform called KLT. And it's optimum in a sense that it does what a transform should do. It has the best compaction property of all the transforms in a sense that the first m coefficients that it produces, that the largest m coefficients that it produces, or the first m, if you rank order them in terms of decreasing order, decreasing size, has the best compaction property than any other transform. And the coefficients are completely uncorrelated. Those are the two desirable properties of transforms that makes us want to use them, right? But unfortunately, KLT, like many other transforms and ideas, is highly signal dependent. It assumes the signal is stationary and assumes that there's autocorrelation for those images. And if you try to adapt if you try to compute the autocorrelation of each image and send the basis functions to the receiver, that chews up too many bits, and so it wasn't really a practical thing. However, what we talked about last time was that if you assume your image assume it satisfies or is a Markov model with a correlation coefficient rho, as rho approaches 1, then KLT reduces to discrete cosine transform. And we were all very happy about that. And as you all know, discrete cosine transform is the basis function that's used in all of the in many of the image processing standards and applications, ranging from JPEG to lossless JPEG to MPEG-1, MPEG-2, MPEG-4, etc. And I wrote down the basic expression for discrete cosine transform. And in today's lecture, I'm going to do several things. I'm going to talk about discrete cosine transform and show why and how it's better than DFT, discrete Fourier transform. Because after all, for those of you who at least been undergraduate at Berkeley, or undergraduates elsewhere who've gone through the traditional signals and systems curriculum anywhere, all you've ever seen in your entire life has been Fourier, 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 and now we come and say, oh, no, by the way, use discrete cosine transform. So when I was first presented with discrete cosine transform, I was very disappointed. And I said, well, all that years of education about Fourier just goes down the drain. But the two things are related, and I'll try to explain why we use DCT over DFT. Then I'll talk about the compaction properties of KLT, DCT, and DFT, and also Walsh-Hadamard transform. And I'll explain what Walsh-Hadamard is. And then I'll talk about quantization of DCT coefficients and the bit allocation stuff. And then I'll show some practical examples of DCT in action. So that's a big agenda, and I think if we didn't have the survey, we could have gotten it all done, but I'm not really sure now we could or not. But let's just get started anyway. So let's bring the camera onto this, onto my sheet. So what we're talking about today is discrete cosine transform, and its use in image compression. Okay. So I want to start by arguing as to why DCT has better compaction properties than DFT. That's the first thing I want to address. And before doing that, I want to kind of remind you about what DFT exactly does. So here's at least the way in the Berkeley EE123 or EE120 series, this is the way we introduce discrete Fourier transform. So you start with a finite length. So x of n we assume is a finite length endpoint sequence. Okay, so what you do is you start with x of n, which could look something like this. Okay. This is the duration of it. And then you build x tilde of n, which is the periodic version of x. So that's x tilde of n. So this is it, okay, as a function of n. And then from x tilde of n, you build its discrete Fourier series. You get another periodic sequence, x tilde of k, and then you take one period of it to get x of k, which is the DFT of x of n. Okay. So right away, if I look at this picture, you can see what the problem is with DFT. If the zeroth sample, this is sample 0 and this is sample n minus 1. So this is 0, n minus 1, n, 2n minus 1, 2n, 3n minus 1, etc. Essentially, if the 0th sample and the n minus 1st sample have entirely different values, when I replicate when I periodicize this x of n to generate x tilde of n, I'm going to get sharp discontinuities in the process of periodicizing. Because at the end, this is the thing I take the discrete Fourier series. So from here to here, there's sharp discontinuities. And it's these sharp discontinuities that results in unnecessary high-frequency coefficients. In DFT. Okay. So essentially, we're replicating x of n, or we're to get x tilde of n, and then to take the Fourier series of this, and in the process of doing that, if we're introducing, it's a matter of luck. I mean, if x of 0 and x of n minus 1 were closed, we wouldn't have that. We wouldn't have it, but now we do. So the question is, but what is one of the nice things we like about this DFT? Well, one of the things we like about it is there's fast algorithms such as FFT that allows us to compute it. So now let's talk about how DCT works and how DCT avoids these sharp discontinuities. And further, let's relate DCT to DFT to convince you guys that we can still use fast algorithms such as FFT in order to compute it. Okay, so how does DCT work? And the answer is, well, generally speaking, you replicate the signal in a better way, so there's no sharp discontinuities. So replicate the signal, and I'll tell you, I put better in a quote right now, and I'll tell you what I mean by that. So that there is no sharp discontinuities. So, for example, if I have a signal x of n that takes on the values alpha naught, alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 for indices 0 all the way to 5, then the way I replicate it is going to be flipping it over like that and adding it here. So let me talk about that. So x of n, I guess the replicated version, let me not name it for now because I'm going to name it in a second. The replicated version is going to be this, and then so alpha naught, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 5, alpha 4, alpha 3, alpha 2, alpha 1, alpha 0. So 0 to 5 here, and then 6, 7, 8, 9, 10, 11. So by reflecting it and flipping it over this way, because alpha 5 is repeated here, I've essentially deliberately, on purpose, by construction, by synthesis, I have smoothly extrapolated the signal. Now I'm going to take the two endpoint DFT of this. And one of the questions you might immediately worry about is, oh God, we used to have endpoint. An endpoint sequence had an endpoint DFT, but now it seems like an endpoint sequence is going to have a two endpoint transform if I do that. But don't worry about that. We can still squeeze it all into endpoints in a way that I'll talk about in just a second. But the key point I want you to remember is going from here to here, there's no longer any sharp discontinuities. Okay, so this is kind of a sketch of how DCT looks like. Now let me tell you precisely how we do this replication and precisely how I can keep it to n coefficients without having a coefficient expansion. Okay, so before doing that, I'd like to say one comment. As I said in the last time's lecture, there's 4 kinds of DCTs. And the 4 kinds relate to how many different ways you can do this smooth interpolation. For example, some people just don't reflect it. They go to 0 and then they bring it up. Sometimes it's odd length, sometimes it's even length, etc. But for most of our discussions, we're going to stick to DCT that's of type 2. Okay, so here's DCT type 2, which is the type we're going to be dealing with. And here's the precise definition of it. XC2 of K is twice, and I'm doing it all in 1 dimensions for the sake of simplicity, summation from n equals 0 to n minus 1, x of n, cosine of pi k 2n plus 1 over 2n. This is the analysis equation, which means you start with the sequence and you get the coefficients. And then you have the synthesis equation down here, which is, you can get back your original signal x of n. Can you roll down, please? As 1 over n, summation of k equals 0 to n minus 1, beta of k, and then now you start with the coefficients, x sub k of c2 of k, times cosine of pi k 2n plus 1 over 2n. And the first thing that you notice when you stare at these two equations is that the forward and the backward have the same expression, which is nice. Even in DFT, the forward and backward, they're very similar. They only have a little difference between the two of them. But as you remember from 123 and other courses, you can use a forward DFT box to do an inverse DFT box by rearranging the input points a little bit and manipulating the input points before you shove it into the forward box. And in this expression, beta of k, this extra thing is just 1 over half when k is equal to 0, and it's 1 when k is between 1 and n. So this is the type 2 DCT that we're interested in, and now I'm going to tell you how this relates to DFT and how is it that it results in replication of a signal in this reflection way that avoids sharp discontinuities. So let's move on to that. Can you roll up there? So, so 2 things I want to say. Relation between DCT and DFT. Okay, so here's, I first make a proposal as to how this definition of DCT type 2 is related to DFT, and then I mathematically prove it in just 1 second. Okay, and the reason it's 1 second is because it's not that complicated. So here's my proposal. Okay, there's actually 2 proposals. It's for the sake of completeness, I write down both of them, but the proposal number 2 is the one that shines light as to why this thing doesn't result in sharp discontinuity. So proposal 1, even though I won't prove it, I'll just like to write down the steps of it. Step 1, start with x of n, which is our endpoint real sequence. We're assuming that our sequences are real. Step 2, compute a 2 endpoint DFT of it to get what we call x of k. And step 3, the coefficients x c2 of k, the DCT coefficients, is just twice the real part of this guy that we just computed, x of k, times an exponential e to the minus j 2 pi k over n. And you can show that can show all these steps that this relationship exactly allows you to go from DFT to DCT. But this is not the insight providing method of computing DCT, even though it is a valid method computationally. So proposal number 2 as to how DCT and DFT are related to each other is as follows. So I'm going to start with an endpoint real sequence. Again, we call this x of n. Then I'm going to pad it with n zeros. And I get the sequence x sub 2n of n. Just I write down 2n at the bottom as an index, just to demonstrate that the sequence is 2n points long. Okay. And then step number 3, I'm going to form a periodic sequence using this x2 of n, which I call x2 tilde of n, and tilde always denotes periodicity, which is the same as x tilde of 2n of n plus x tilde of 2n of minus n minus 1. So I start with this 2n point sequence. I make that periodic to get x tilde, and then I add the 2 versions of x tilde to n in order to get a new sequence. And I'll pictorially explain to you what happens in just 1 second. Yeah.
This might be trivial, but does it matter where you add the zeros?
Oh, what I meant to say is the next n points. So if the index of x of n goes from 0 to n minus 1, I pad zeros as n plus 1 all the way to 2n minus 1. Should I write that down? Okay. I never thought about the confusion that could cause. Okay. And then number 4, take now the 2n point DFT of 1 period of x tilde 2 of n, and call that x2 of k. This is, and now this is the DCT. This is xc2 of k. Okay. So to show you kind of a pictorially, first I'm going to show you pictorially what this corresponds to, so you get an intuition as to what's going on, and then I'm going to show you mathematically that this is indeed true and it's not something magical. So pictorially, what we have, if you can roll up the camera a little bit, okay, is the following. Let's say I start with x of n, and I have samples 4, 3, 2, 1. And suppose then that I build now x2 of n, which is this guy, x2n of n. Okay, and what is that? Well, it's 4, 3, 2, 1, and then 4 zeros. 0, 0, 0, 0. So I've padded it with 4 zeros, right? Now I'm going to build this periodic version of x2 of n, which is x2 of n tilde. So if I do that, what do I get? x2 of n tilde. Well, it's this 8-point sequence repeated here, here, etc. So let's just do that. 4, 3, 2, 1, 0, 0, 0, 0, and then 4, 3, 2, 1, 0, 0, 0, 0, and etc. 4, 3, 2, 1, 0, 0, 0, 0. So this is x2n of tilde, the periodic version of this guy. Okay, and the next step is from here to use this x tilde 2n guy added to x tilde 2n of minus n minus 1. So pictorially, let us plot x tilde of 2n minus n minus 1. How does that look like? Well, x tilde 2n of minus n minus 1. Well, that thing is going to look like, almost the same thing as this guy, except that the places where it's got zeros, this guy has 4, 3, 2, 1. So it's going to have 4, 3, 2, 1, 0, 0, 0, 0. And then it's going to have 4, 3, 2, 1, 0, 0, 0, 0. And it's going to have 4, 3, 2, 1, 0, 0, 0, 0. Okay? And now if I add these two guys together, what do I get? As a function of n, I get 4, 3, 2, 1, and then 1, 2, 3, 4. Okay, and add this guy to this guy, so I get 4, 3, 2, 1, 1, 2, 3, 4. Okay, 4, 3, 2, 1, 1, 2, 3, 4. It's on and on and on. So this sequence here is just x tilde of 2n of n plus x tilde of 2n of minus n minus 1. This is what this sequence is. Okay? And so by now it should be clear to you that picture that I drew at the at the second page of our lecture, that this reflection business that I was talking about here, right? Essentially, this x tilde of 2n of n plus x tilde of 2n of n minus n minus 1, I mean, a lot of complicated symbols. All it means is I just flipped it, and I replicated it. Now, what my recipe here says, now that I formed this long sequence in step 3, which is shown pictorially here, all I have to do is take a 2n point DFT of this sequence. Okay, so the idea now is, I'm going to page 5 here, all I have to do is take the 8 point or 2n point DFT of this sequence. Okay? Okay? So, right. So you can see that because now I'm taking a DFT of a sequence that doesn't have these sharp discontinuities, no sharp discontinuity. I'm not going to have any high frequency kind of a signal. I'm not going to have any high frequency coefficients in my DFT, and therefore my DCT will also not have high frequency coefficients. So to prove to you mathematically that these steps are identical to the definition of DCT, let me just show that. Show that proposal 2 actually works. Let's do that really quickly. Let's see, do I have that set of notes? Yeah, actually I don't. Yeah, I don't have the. I have the proof of. Yeah, I didn't bring that with myself, but I have the proof of how and why this step works, but I didn't bring the proof of this but with me. But the proof you can see is pretty straightforward. Pretty much all you have to do. Actually, hold on one second. No, I do. It's pretty straightforward. So so the question that we have is in this diagram, we're going to ask ourselves, how is this x2 of k related to, after I take the two endpoint DFT of one period of this thing and I get this new sequence x2 of k, how is it related to the DCT? So how is x2 of k in this proposal related to xc2 of k? Are they the same thing or not? So in other words, I'm putting question marks here, right? So let's quickly go through that calculation. So start with x of n and call x of k to be the two endpoint DFT of x of n. That means you start with x of n, you've padded it with a bunch of zeros to get, in this case, to get x2 of n. And so call this x of k is the two endpoint DFT of x of n, which is essentially also the two endpoint DFT of x2 of n, the same thing. Okay. It's also the two endpoint DFT of x2 n of n, because these two things are, this is just a padded version of that. So to get a two endpoint DFT of x of n, you just pad it with n zeros and do that job. So again, can you roll up just a tiny bit, please? I want this procedure to be in great, thank you. So having said all of that, how can we write the expression for x2 of k? Well, x2 of k is a two endpoint DFT of x2 tilde, and x2 tilde is this plus that. So applying the shift property of discrete Fourier series and also the conjugation properties, you can write x2 of k as just x of k, which is the two endpoint DFT of this guy. You're applying the linearity property. So it's the DFT of this guy plus the DFT of this guy. So the DFT of this guy is nothing but x of k, because it's a two endpoint sequence, and we just called the two endpoint DFT of x of n as x of k. So that's that. Plus, and the DFT of this guy, well, there's a minus 1 here that causes an exponential, e to the j 2 pi k over 2n. And then there's x2 tilde of minus n that causes this thing to get conjugated, x tilde complex conjugate of k. Okay? So by inspection of these steps, you can write down x2 of k as this expression down here. And then the next step is is just algebra. You factor out e to the j pi k over 2n outside, and what you get is x of k times e to the minus j pi k over 2n, just to cancel this guy out, plus, and now you have e to the j pi k over 2n of x complex conjugate of k. Why did I do that? Well, because I wanted to generate two quantities inside the parentheses, inside the brackets, that are complex conjugates of each other. And the way to do that is to bring half of this out and write it down as this way. How did I know about this trick? Somebody else invented it many years ago, and I've just been teaching it for the last 18 years. Okay, so this is x2 of k, and now we can keep writing this thing down. It's e to the j pi k over 2n. And what is this thing? Well, you're adding two complex two things that are complex conjugates of each other. This is twice the real part of this thing, x of k times e to the minus j pi k over 2n. Okay? And this thing, based on our proposal 1, which I never proved to you, but I'm hoping that you accept in blind faith, is xc2 of k. Okay. Therefore, x2 of k is just e to the j pi k 2n times xc2 of k. Therefore, I made a mistake saying here x2k is exactly xc2 of k. There's an exponential that I dropped. So it's not just that. So there's advantages in doing proofs. It allows you to catch all your mistakes. Okay? So once you there's got to be a step 5 here, right? And the step 5 is what? To get xc of k, you have to get x2 of k and multiply e to the minus j pi k. So step 5, get xc of xc2 of k is just x2 of k times the e to the minus j pi k over 2n. So this x2 is related to the dct. Through that exponential, you got to undo the exponential this way. And if we do that, then that means that xc2 of k is just x2 of k times e to the minus j pi k over 2n. Okay? So this is it. This is showing how we can use DFT. So remember, this is just a DFT, but it's not the DFT of the original sequence. It's the 2n point DFT of the original sequence. Okay. Actually, that's not even true. 2n point DFT original plus the reflected one. Okay. Okay. So, is anybody worried about anything? Have I shown all the things I promised to show you? So, I mean, mechanically, let's just go through this, right? I have an n-point real sequence, and it's just n numbers, right? And I could either take its n-point DFT, which gives me n numbers, n complex numbers. That would be its DFT. Or what I'm telling you is start with the n-point sequence, flip it over, get a 2 n-point sequence, take a DFT of the 2 n-point, the whole thing, after I reflected it, get x2 of k, and then multiply by exponential, and I get xc2 of k. How many points is the x2 of k? Yeah, how many points is in xc2 of k? You would seem it's 2n, and you would seem that we messed up, right? If you started with an n-point sequence, now our sequence is 2 n-point sequence. No need to worry though. Why? Why is it that only n point of this is enough? Why is that? Because I started with a real sequence, right? And x2 of n, this x2 of k is a 2 n-point sequence of a real symmetric. This is what we're taking a 2 n-point DFT, right? It's positive, it's real, and it's even. It's symmetric. So its DFT is going to be real and symmetric. So half of it is enough. So they're not really 2n independent numbers in x2 of k. Half of them are a repeat of the other half. So it's still... So it's still an endpoint. We're still okay by keeping the first n coefficients of this guy. So even though x2 of k has 2 n coefficients, we only need to worry about the first n coefficients of it, because it's a DFT of real and even sequence. Remember, real even sequence results in a real even transform. So everything is good. Okay, any questions? All right, let's talk about compaction properties of DCT. So next I'd like to show you, let me just write down here, figure 8.29 from Oppenheim and Schaefer. If you can zoom into this. Okay. Great. So what this is it's primarily for one-dimensional sequences, but we'll get into the 2D case in just a second. This is the basic thing that illustrates a point. You have a 32-point sequence, and you do this. You take the DCT of that 32-point sequence, DCT type 2, because that's what we covered, and then you take the 32-point DFT of that same sequence. And you start setting coefficients to 0. As you all know, when you take a DCT or DFT of a coefficients, the ones near DC have very high values. As you go away to higher and higher coefficients in AC, they become close to 0. So there's a natural rank ordering of them for most sequences, right? So for example, this point corresponds to the mean square error, and I'll explain what mean square error is, between where you, let's say this point here, at point 5, you set the 5 smallest coefficients in DCT and DFT equal to 0, and then you take the inverse transform, you get a new sequence, and subtract that new sequence from the original to compute how much error you committed. Is that clear? So the solid curve corresponds to the DCT, and the dotted the open circle dotted line or dashed line corresponds to DFT. So you can see that all the way to 25 coefficients, for example, the amount of mean square error introduced by DFT is so much higher than DCT. So in a DCT transform, if you drop 25 coefficients to 0, you're essentially committing no crime. There's no error, almost no error in the mean square error reconstruction, whereas for DFT it's very high. So it's only after you get to these very high value coefficients that they become in par with each other, right? And at DC, when you drop all coefficients, sorry, at the very end, when you keep all the coefficients, they both do perfect reconstruction, right? Because you've kept 32 coefficients for DCT, 32 coefficients for DFT. When you take the inverse, you get the exact same thing. So this point is identical, and at this point they're identical. Well, should they be identical? Yeah. Because I said the reverse. This point means that no coefficients have been set to 0. So that means this is perfect reconstruction at this point. So this point should be the same. Here, all the coefficients have been set to 0, so they also perform the same. So at the two ends, they perform the same, but you can see that DCT has a much better performance characteristics. Is that plot clear? Okay. Next, I am going to show some addition. Let me get my notes here. The next I'm going to show some more plots of DCT. So let me number this thing. So this was page 6. We call this page 7. And we call this page 8. Okay? So next, if you can zoom into this picture, this is a plot from a book by Netravalli and Haskell, I think. That's right, Netravalli and Haskell. And what I'm showing you is, again, now this is not showing error, it's showing the peak signal to noise ratio. It's the opposite of error, how good of a reconstruction quality we have, using different transforms, KLT, DCT, Walsh-Hadamard transform, which I'll explain in just 1 second. I didn't want to cut the flow here, and also DFT. And what's on the x-axis is the fraction of the coefficient sent. Okay, if you start with a 4x4, you start with this picture Karen, which I have a little snippet of it. Let me just show it to you here. This is Karen. I'm sorry, it's a Xerox of a Xerox of a Xerox, but it gives you roughly what we're looking at. So you divide it up into 4x4 blocks, and then you keep this percentage of the coefficients. Here you keep 100% of the coefficients, therefore signal to noise ratio is its highest. And here you keep 0% of the coefficients or 20% of the coefficients. The signal-to-noise ratio is much lower. And this kind of compares the different schemes. And I guess the main point I want to show you is that DFT is much worse than DCT. Furthermore, DCT and KLT are very close to each other. But here, KLT assumes that we're decomposing along the bases, and the bases are known. Whereas in real life, for that image, whereas in real life, that the bases for that have to be transmitted. The same thing here, if instead of doing 4 by 4 blocks, you do 16 by 16 blocks. So this axis is the percentage of the coefficients that are sent, and this is the signal-to-noise ratio. Okay? So we call that page 8 of our lecture notes, because I want you to have a record of all of these on the web. And this last thing here is page, we'll call this page 9 of our lecture notes here. But this is, now we're doing a different experiment. We're having different block sizes. So one of the questions that you will be asking yourself is, well, in all of these experiments, you have 4 by 4 blocks, and you have 8 by 8 blocks, and 16 by 16 blocks, or 2 by 2 blocks. How do I know what the optimal block size is? And this plot, to some extent, addresses that. Let me backtrack here. Initially, when DCT was invented, people couldn't apply DCT on the whole image because it was just computationally too difficult. It required too much computation. So initially, it was a computation issue. But also, it's not purely that. You could argue now that there's plenty of fast computers. Why don't we do large, the entire image size? The reason is that there's a law of diminishing returns. So in this plot here, you look at the truncation PSNR, where you keep 60% of the coefficients, but the block size changes. So here your block size is 256, which means you have 16 by 16 blocks. And here your block size is 16. That means you have 4 by 4 blocks. And these are other block sizes. And as you can see, the efficiency is very low for small block sizes. But as you increase to 10 by 10 or 16 by 16, you get improvement. And so in practice, most of the time when people do DCTs, at least in the 80s and 90s, they would use a 16 by 16 block. Okay? Yeah, this is PSNR, meaning the quality improves the higher this number is. The word truncation, I think, is a little bit confusing here, but it is the quality of the image. Okay? Okay, so next, I would like, let me go back to my lecture notes to remember what order we were going to do things. So next, what I want to talk about is one more picture along the same lines. In particular, figure 8. Let's see. Yeah. Figure 830 and 833 from Gonzalez and Woods. So let me just do that. So let's go back to the machine here, and I think it's this one, correct? Okay, so the first thing I want to show you is, which is something I haven't done that yet, is this is how DCT coefficients, I'm sorry, this is how DCT basis functions look like. Did I show this to you last time? Yeah. So, oh yeah, I think we did show it. So these are, 4 by 4 blocks, and it shows the DC basis function, and as in this direction, the vertical frequency increases. In this direction, the horizontal frequency increases, and right here you have the highest vertical and and horizontal frequency. So if you had 4x4 blocks, an arbitrary 4x4 blocks, you're essentially writing this as a linear combination of these guys. Okay? And if you do that, what do you think could go wrong or might go wrong? Well, these are highly blocky looking functions. So if you write a new signal as a linear sum of blocky looking functions, that signal is going to be blocky looking, right? The blocky looking structure of this, because at the end of the day, if I write an arbitrary 4x4 image as a linear combination of those, if my coefficients, so it's a precise relationship, right? In a sense that if I have the precise weight of each of these 16, I've projected my signal in this 16-dimensional space, and I know the exact component along each of these 16 basis functions. So if I combine them precisely, I get the signal back precisely. But in real life, what happens? The coefficients get quantized, right? Because if you don't quantize the coefficients and express them as a real number, you'll have to use infinite precision, like, lots of numbers after the decimal point, and lots of bits to represent that infinite precision number in order to precisely reconstruct the signal. So in real life, coefficients get quantized, and therefore, because of that quantization, the error that results in is a linear version of these blocky-looking functions, and that makes your final signal to be blocky. And we'll talk about that in just a second. But just so that you're aware, this is the basis function for Walsh-Hadamard. And if I get a chance, towards the end of the lecture, I will spend a little bit of time mathematically writing down the expression for these basis functions, just so that you know how they look like and what they are. What this is showing is the woman signal from Gonzalez and Woods. If we apply let's see, Fourier transform, Hadamard transform, and DCT, and we keep, let me tell you precisely, I think it's 50% of the coefficients. Yeah. So we keep the 50% highest coefficients, and we're left with the other ones. Again, I don't know if this comes across on TV or not, but if you look at the book, for example, you can see there's quite a bit of errors here and here. Do you see that on the TV screen?
No.
Here and here? No. Okay. It is in your books, and then for Hadamard, it's a little bit less. And then for DCT, it's the least. So this picture kind of shows what we talked about already, and this kind of shows the root mean square error as a function of sub-image size, which we already showed another version of this. So if you do 2x2 blocks versus 4x4 versus 8x8, 16x16, and 32x32. And as you can see, the Fourier has the largest amount of error, followed by Walsh-Hadamard, followed by cosine. But the thing to notice is that as the block size increases, the mean square error, and in this case, we're keeping, let's see, 25% of the coefficients. So in the case of 2x2, we're keeping one coefficient. In the case of 32x32, you're keeping 25% of 1024, which is 250 coefficients. So you can see there's a law of diminishing return as you move from 16x16 to 32x32. So for most applications, 16x16 is just about good enough. And what you see in this picture is, once again, this is a piece of the woman picture that we have zoomed in of the original, okay? And this is applying 2x2 and keeping 25% of 2x2 DCT blocks and applying 25% of coefficients. This is 4x4 and this is 8x8. And you can also see visually, you can also, I don't know if you see, do you see the blockiness in this thing? Okay, that gets through. So this is an agreement with this high mean square error here that we get. So 2 by 2, not only from a mean square error, does worse than 16 by 16, but or 8 by 8, but also from a visual point of view, you can see that if you keep 25% of coefficients, 8 by 8 does a lot better than 2 by 2. All right? And I think that's kind of where I want to stop in terms of the Gonzalez and Woods pictures are concerned. So the next thing that I want to talk about, let me just quickly write down the Walsh-Hadamard transform, just so that because I talked about it and I showed pictures of it, it might be useful to have an expression of it. So okay, just for the sake of completeness. So in general, if the coefficients of a transform are given by the signal f of x comma y times the kernel of the transform g of x comma y comma u comma v, where x and y range from 0 to n minus 1, then for Walsh-Hadamard, g of x comma y comma u comma v is given by 1 over n times minus 1 to the power of this huge summation, I from 0 to m minus 1 of can you zoom out a little bit? The floor function bi of x times p sub I of u plus b sub I of y times p sub I of v. Okay? Where n is equal to 2 to the m, so this number here is m, and the summation in the exponent is performed in modulo 2. Oh, I see what you mean. I might have made a mistake. Hold on. Let me quickly look it up. They're all I's. Okay. Sorry, which one did you ask? This one?
No, like in the original for capital T, like what's F and G here?
F is the signal. G is the kernel. Yeah. Like for DCT, for one-dimensional DCT, that's the kernel. It has k's in it and it has n's in it, right? And for Fourier transform is e to the minus j 2 pi k over n. This is the kernel for Hadamard, and it's defined as this. It's got x and y because I've gone to 2 dimensions and I've introduced two x and y as the space domain variables and u and v are the frequency domain. Got you? So summation in the exponent is modulo 2. Okay. And now I have to define all these extra things. Okay, b sub k of z is just the kth bit from right to left in binary representation of z. For example, when m is equal to 3, z is equal to 6, and the binary representation is 1, 1, 0, then b0 of z is 0, b1 of z is 1, b2 of z is 1. And now I have to define what these pi's are. Okay, roll back please. So pi of u's are defined as follows. p0 of u is bm minus 1 of u, and then p1 of u is just bm minus 1 of u plus bm minus 2 of u. p2 of u is bm minus 2 of u plus bm minus 3 of u, da 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 da, all the way to pm minus 1 of u is b1 of u plus b0 of u. Okay? So, I mean, this is a lot of lengthy description, and all that really matters that I want you to remember is that the picture I showed you, the Walsh-Hadamard transform, is a binary looking thing that that has those stripes back and forth. Okay. And I would like to end today's lecture. Did everybody copy this? Okay. With one more result from scalar quantization of a vector source, which I wanted to have covered after Huffman coding, but never did. But once we cover that, then next time's lecture we'll talk about quantization of DCT, how JPEG works, put everything together and show an actual compression system in action. So let's do that. So let me motivate why I'm covering this, right? So let's take a back seat. What are we doing? We have a big image. We already decided we're going to divide it not into 2 by 2 blocks. 2 by 2 is not too efficient. Let's say 16 by 16 blocks. We already decided DCT does better than Fourier transform and does better than Hadamard, and in the limit, as rho goes to 1 for Markov images, it becomes as good as KLT. Good. We're settled on our transform, DCT for now. You take 16 by 16 DCT of your blocks, and you get numbers. Okay? Then you have to do quantization and bit allocation. And we've already talked about the fact that in practice nobody ever does non-uniform quantization, because uniform quantization with appropriate entropy coding like Huffman or arithmetic coding is always as good or better than non-uniform quantization. So let's do the simple thing of uniform quantization. But once you do that, how do you, and suppose that somebody has told you this image has got to get quantized and compressed to X bits. You have a total of, I don't know, 1,000 bits. You're designing a web page, and you want to address it, you want to address the DSL community, and you want to address the dial-up guys, and somebody has magically come to you and said the total number of bits is X. How do you decide how to divide those X bits between different sub-images in the block, and also within each sub-image? Suppose you decided to come up with a simple algorithm that each sub-image is going to have Y bits. How do I decide, how do I distribute those Y bits among all the DCT coefficients? What's the optimum bit allocation strategy? Essentially, I have 256 DCT coefficients, and how would I go about doing that? There's a fundamental result in compression that keeps coming up, no matter if you do DCT quantization and bit allocation, subband coding and bit allocation. Doesn't matter what you do, and that's what I want to cover now. So the question is scalar quantization of a vector source. And this is just a fancy name for just saying, look, I got an 8 by 8 block, for example, 64 coefficients, and I have X bits to divide up, to divvy up among the coefficients. How do I do that? How do I do the optimal bit allocation? And in this discussion, I am completely ignoring psychophysical, psycho effects of, oh, the eye is more sensitive to low frequency coefficients, therefore we have to do something special for that. We're ignoring all of that. Now we're just strictly formulating a mathematical problem. So essentially, here's the setup. I'm going to assume that I have n scalars, f sub i's, and these guys range from n to 1. Okay? And I'm going to assume that each f sub I is quantized to L sub I reconstruction levels. Okay? And I'm going to assume I have a total of b bits to encode the n scalars. And for the sake of, okay, and let's roll up just a little bit. And here I'm talking about optimal bit allocation. Every time you talk about optimum, you have to say what your metric is. Otherwise, you're shooting in the dark. So the optimum bit allocation, what do I mean by that? Strategy depends on two things. Um, A, what the error criteria is, and in this case, as you see, we're just going to use mean square error. And B, it's going to depend on the PDF probability distribution function of each of those random variables, F1, F2, all the way. Okay? And so, okay, if the optimum strategy depends on those, let me just tell you what our criterion is. So here's our error criteria. We're going to minimize what else? Mean square error, because that's the best thing known to man to minimize. And it's defined as summation from I equals 1 to n of expected value of this whole thing squared, f sub I minus f sub I prime, where f sub I prime is the quantized bit allocated version of f sub I, right? So we want to minimize this quantity subject to with respect to b sub I, which is the bits allocated for the ith scalar, where b sub I is defined as the bits allocated to the ith scalar, that is f sub I. So we're giving b sub I, we're assuming that we give b sub I bits to f sub I. We want to know what the b sub i's are. How many do we give? 5 bits to f1, 3 bits to f2, 10 bits to f3? How do we divide these bits? Kind of a resource allocation problem, right? Same thing as like a department chair faces. I have this much budget. I got to make the undergrads happy, the grads happy, the professors happy. How do I divide up the money or the resources between these groups? So that's the same thing we're doing, okay? So in terms of PDF, to be able to solve the problem, I'm going to assume that the PDF of all the FIs are the same, except that they have different variances. So they have the same shape. They're all Laplacian, or they're all Gaussian, they're all uniform. They all have the same shape, but they have different variances. Except that have different variances. Now, for the sake of moving this argument ahead and proving something mathematical and being able to make a precise mathematical statement, even though, as I said, in practice we don't use Lloyd-Max quantizer, which is non-uniform, but just for the sake of deriving this result, we're going to assume that we use one more assumptions, Lloyd-Max quantizers, in order to come up. Remember, we were assuming Fi is quantized to Li reconstruction levels. We're assuming that we use Lloyd-Max quantizer to do that. So having assumed all of these things, I don't know, it was a long list of assumptions, you can solve a mathematical programming problem, essentially a Lagrangian optimization, which I won't go into it, Lagrangian optimization, to show the following, to arrive at the following result. That b sub I, the bits allocated to the ith random variable, is equal to b over n. That means get the total number of bits, divide it equally between all the n random variables. And by now you might be disappointed and say, oh, why are we doing that? No, but there's another term. Plus 1/2 log of sigma I squared over the product from I from 1 to n of the product from j from 1 to n of sigma squared j, the whole thing to the power of 1n. Okay? Where sigma I is the variance of f sub I. Furthermore, so here's can show. Number one, And number two, we can show the following, that L sub I is also given by, can you roll up just a little bit? And L sub I, which is the number of reconstruction levels for Fi, is given by the following. It's sigma I over the same thing in the denominator. Product from j equals 1 to n of sigma j to the power of 1n, 2 to the b over n. Okay? So if you can roll up just a little bit to have both of these things, great. So these are the two main results. And let me just spend a second or a minute to interpret them. Does this make sense? Yeah, what it says, this quantity in the bottom is just a normalization thing. B sub I, the number of bits we give to the ith random variable, is some fixed quantity, as if we had distributed it equally, plus some other quantity. And that other quantity has sigma squared I. That means what? That means the higher the variance of that random variable, the bigger the energy it has, the more bits it gets. That means if I have two random variables, one has variance of 10, the other one has variance of 2, the guy with variance of 10 gets a lot more bits than variance of 2. So subject to the fact that all the n random variables have a total of b bits, there's n of them, they have the same PDF, in order to minimize mean square error for reconstruction, assuming that we use Lloyd-Max